It looks like fuel, smells like fuel, not drilled from the ground though. It was manufactured by the company, as you say here, in this tiny little unit on an industrial estate near Stockton-on-Tees. So like you say, the question today is, if this can be manufactured, could it help in the battle against climate change? Could it be helped to solve the world's fuel crisis? Let me show you very quickly how it's made. We come inside this unit here. The glasses are on, so clearly I'm going to be talking some science. This is methanol in this tank here, which the company has manufactured. It's mixed with something called DME, which is an alternative to diesel that is used to fuel things like public transport in places like Sweden. It's then distilled, and this is where the fuel comes out of this tank here. Let's speak now to the chief executive of the company here, Peter Harrison. Efficiency. This is what the scientists are asking today. As we heard a minute ago, it sounds too good to be true. So how long does it take to, say, make a litre of this fuel?
The unit we have here is a demonstration facility. So we're using existing technology to bring all this together and to demonstrate that we can make all these processes work together. So this is not an efficient site. That is something that we will develop in the next project.
But I guess when you're evaluating how good it is, that's something you have to look at. So how much does all this cost?
So far we've had a 2-year project and we've invested £1 million to get where we are today.
OK, what's the next step then?
Right, well we've got a design now for a 1 tonne a day unit that will be in 3 containers, and we expect to be in production by 2015 making synthetic petrol.
So who are you aiming this at?
The petrol that we're making is a very clean designer fuel, and it's targeted initially at people in the motorsport sector for use in performance engines.
How much does it use? How much energy do you use to create this?
Well, petrol is a highly energy concentrated product, and so we're going to be using renewable energy and capturing that to put into our product.
And capturing it, that's the key thing, isn't it? It's all about capturing this energy.
Yes, it's an energy store process which is carbon neutral and can fight the climate change issues. OK,
Peter, thank you very much for explaining that to us here today. So we may be a long way off yet before we start putting this in our cars, but clearly what they are saying on Teesside today is this isn't production, it's demonstration. So let's try and use what we have created here to perhaps solve energy problems in the future.
Good morning, Steve. Hey, Nathaniel, how are you? Doing just great. Go ahead, Steve.
Auto driving.
Here we go. Away we go. Look, Ma, no hands.
No hands anywhere.
No hands, no feet. No hands, no feet. No nothing. I love it. So we're here at the stop sign. Yep. Car's using radars and laser to check and make sure there's nothing coming either way. I find myself looking. Old habits die hard, man. Hey, they don't die. Hey, anybody up for a taco? Yeah. What do you want to do today, Steve? I'm all for Taco Bell myself. All right. Well, let's go get a taco at the drive-thru. And we're turning into the parking lot. Yep. How neat. Go. Now we kind of creep along here. Does anybody have any money? I've got money. No, I've got my wallet right here. You roll down your window and order a burrito. Yeah, push that up. I'm doing very well. How are you today? This is some of the best driving I've ever done.
95% of my vision is gone. I'm well past legally blind. You lose your timing in life, everything takes you much longer. There are some places that you cannot go, there are some things that you really cannot do. Where this would change my life is to give me the independence and the flexibility to go the places I both want to go and need to go when I need to do those things.
Get out. I've got places I have to go. You know, so, you know, anyway,
Bye now.
It's been nice. You know,
Yeah.
it's been nice.
We propose a complete process for designing, simulating, and fabricating synthetic skin for an animatronics character that faithfully mimics a given target subject and its expressions. The goal of our work is to automate this process, to increase the realism of the resulting character, and ultimately, to create an animatronic face that closely resembles a given human subject. In order to accomplish this task, we capitalize on recent developments from 3 areas in computer graphics: facial performance capture, physics-based simulation, and fabrication-oriented material design. The process starts by capturing 3D facial expressions for a given target subject. This data provides information about the deformation behavior of skin. In addition, we also determine the operational range of the animatronic head, which consists of a set of skin attachment links actuated by motors. We then measure elastic properties for a collection of different materials used to manufacture synthetic soft tissue. Given all of these measurements, we employ physics-based simulation to predict the behavior of any soft tissue made from these materials, and our optimization process uses the simulation to determine the geometry along with the actuation parameters in order to best match the target expressions. We demonstrate this process by physically cloning a real human face onto an animatronics figure. We use a video camera array and current state-of-the-art performance capture techniques to reconstruct 3D facial geometry of a target subject. The result is a detailed, compatible mesh sequence with explicit temporal correspondence, allowing us to analyze the deformation of a face under various expressions down to the level of individual wrinkles. Our base material for the synthetic skin is silicone. In order to determine the material parameters for the skin simulator, we experimentally acquire force displacement samples of materials of different stiffness. We then optimize for the geometry and actuation parameters in order to best match the target expressions using a single optimization framework. Forward simulation allows us to accurately predict the deformed shape of a given synthetic skin and the resulting forces induced by the moving skin attachment links. Here, the optimization is converging to the best skin thickness for a forehead patch in order to produce a desired expression. After having optimized the ideal skin geometry, we create a mold for pouring the silicone. The mold consists of a core resembling the inner surface of the skin and 6 outer parts that can be removed for extracting the cured skin when it's complete. After mixing the silicone with the corresponding catalyst, it has a liquid consistency and can be poured directly into the mold. We use a pressurized gun to inject the silicone. Approximately 7 days of room temperature curing is required until it is ready to be used. We showcase our complete pipeline by physically cloning a human face for an animatronic figure.
Do or do not. There is no try. Why are you trying so hard to fit in when you were born to stand out? Do or do not. There is no try. Why are you trying so hard to fit in when you were born to stand out? Do or do not. There is no try. Why are you trying so hard to fit in when you were born to stand out? Do or do not, there is no try. Why are you trying so hard to fit in when you were born to stand out? Do or do not, there is no try. Why are you trying so hard to fit in when you were born to stand out?
In this work, we have presented a complete process for designing, simulating, and fabricating synthetic skin for an animatronics character that faithfully mimics a given target subject and its expressions.
Hey, what is up guys? I'm KBHD here. We are back, and this is Google Glass. Now, something that a lot of people ask when, you go out and walk around with this thing on your face, a lot of people ask the same set of questions. One, what is glass? What is that thing on your face? Two, what does it do? And three, what does it look like while you're wearing it? What do you see through glass? So, without any further ado, let's go ahead and take a look. First of all, this exact model that we're looking at is the Explorer edition of Google Glass. And that's a bit more important than a lot of people realize. Basically, this is not the final version of the product. There will be an evolution in software and hardware before an actual consumer edition is created. In fact, there's been several software updates already. But for now, the Explorer edition is a limited edition early version for people willing to go out and explore and give feedback for Google about Glass. Aesthetically, it's a pretty interesting little device because it sits on your face like a regular pair of glasses, but, well, there are no actual lenses. There's no glass in Google Glass except for this prism here. And the other thing about it that's different is it's asymmetrical. So typically, when you're wearing glasses, there's the same thing on both sides. With Glass, all of the smartphone components and all of the things in Google Glass that make it what it is are all on your right-hand side. Now, while Glass does have mostly smartphone insides, what it doesn't have is a cellular radio, which means it can't connect to data by itself. So what it does do is connect to either Wi-Fi or Bluetooth tethering to your smartphone and connect to the My Glass app on your Android or iOS device. And that's very important because without it, you wouldn't be able to do anything on Glass unless you had a device with you connected to it. So this is really what's going to power Glass and make it do all that it does when it connects to the internet and pulls any sort of data. So how does it actually look to be looking through the actual prism in Google Glass? Well, Google says that it's supposed to look approximately like a 25-inch display from 8 feet away. So if you have a 25-inch computer monitor, back up your chair, roll back 8 feet away, and that's about what it'll look like. Now, it's obviously not an HD display. In fact, it's around 640 by 360. But the idea here is that this is all that you look at when you interface with Google Glass. So it's pretty important. Essentially, it's a square that is fixed in the upper right side of your vision. It's not in the corner. It's not totally crazy, like hard to reach stretch with your eyes bad, but it's definitely out of the way, so it's not going to be intruding your vision all the time. So when looking through the prism, it'll look about like that. That's about right. So when wearing Glass, natively, Glass by itself can do 7 things with it. You can do 7 things. You can take a picture, record a video, navigate somewhere, send a message, call someone, Hangouts, and Google. But let's not forget that this is the, like we said, the Explorer edition of Google Glass, not the final consumer version. So the list of things that it can do is limited, but the idea here is that this is a new form factor. This is the beginning of a new sort of paradigm. We have Android phones, that's one form factor. We have Android tablets, that's another form factor. We'll have a whole bunch of smartwatches soon, that's another form factor. Glass, which is a wearable tech on your face, is a totally different form factor. So think of this as sort of like an Android phone with no apps on it. Out of the box, it can do, you know, a sort of core set of functions, and that's normal for an Android phone. That's a small list of things it can do out of the box. But once you add an app store, once you add the connectivity that a whole bunch of developers and a developer army kind of support, that list of things is going to get a lot longer and a lot more interesting. There are a few officially supported third-party apps right now for Glass, you know, Twitter, Facebook. There's a New York Times app for sort of pop-up news alerts. But in the Glass Explorer community, there's a whole bunch of developers doing their thing and making a ton of different apps for Glass. And of course, when there's a final release where pretty much anyone can develop for it and anyone can buy it, that sort of mainstream apps are kind of a no-brainer. Expect to see a YouTube app, an Instagram app. These kind of things are pretty much undoubtedly going to come to Glass when it's finally available for everyone. But back to those 7 things. Those 7 functions of Google Glass are really not all that different from the core functions of an Android phone without any apps installed. If you bought a Nexus 4 and never used anything in the Play Store, you'd get a pretty similar list of things that you can do with it out of the box. But again, like we said, this is the Explorer edition. Many more things are going to be added. Now for a brief rundown of these 7. Okay, I'm going to go through all 7 of these things. First of all these things are going to be done with an interaction with the trackpad on the side of Glass. So there's a swipe forward, backward, down, and a tap. And this actually feels pretty natural with the sort of light tapping. You're not really bashing it against your own head, but you're just doing slight swipes and light taps and things like that. And that feels normal. So number 1, you can take pictures. So you can say, okay, Glass, take a picture. Or if you don't want to do that at all, you can just tap that photo button that's on the top of Glass, and I just took a picture of you, the camera, and the light. So that's what you look like right now. And if I want to take a video, that's the next function of Glass. Of course, you can say, okay, Glass, record a video, and you'll start recording a video. Or you can actually hold down the photo button on the top of Glass, and you automatically start taking a 10-second video. So you're going to start looking at what I'm seeing, which is basically a bunch of lights and a microphone. But yeah, that's what it looks like to take a video with Glass. It's automatically going to take a 10-second video, so if you want to extend it, you have to tap the photo button again, and you'll get like an unlimited recording time until like the battery dies, until you stop recording. The photo and video quality are really pretty good, and this is one of the defining features of what makes Glass so special, because it's basically a first-person look at what someone's actually doing. Now it's a little bit above your field of vision, so if you were like handheld gaming or something like that, you kind of have to look down a little bit to get it in your field of view. I found the most part though, most of the things that I do with Glass are pretty amazing, and you would never be able to get any sort of camera angle like that doing anything else, especially because you have both your hands free, which is cool. The video quality is also really good because it's such a wide-angle lens. It uses very similar optics that the Galaxy Nexus did, but that doesn't stop it from being really quite good. And also the photos that I took, again from that first-person view, were really good because it takes a burst of, I think, 10 different shots of a bunch of different exposures and gets a really nice high dynamic range shot. And again, that combined with the wide angle makes it look a lot like what you would see out of the human eye. So it's really, really close to first-person view of what regular people look at. So the third thing Glass does is walking directions, driving. It's just navigation with Google Maps. So you can say, okay, Glass, get directions to, and then say wherever you want to go, B&H for example. And it'll give you the directions and an actual real-time arrow where you would be going on Glass with, you know, the directions to where you're going. You can do walking navigation, biking navigation, and driving navigation. And I think this is actually probably the most awesome of the built-in features in Glass, because if you're in an unfamiliar place and you don't really know where you're going, you move your head around and you get to see the exact direction of the orientation of the arrow change, and you can just literally follow the arrow in Glass to get where you're going, and that's really powerful stuff. Now 4 and 5, you can send a message or place a call using Glass, and that's because it's tethered to your phone with the My Glass app, so you have a certain list of your starred contacts that you can dial whenever you want. So you can say, okay Glass, send a message to John, I'll be late, I'm in traffic, see you in 20 minutes. Or, okay Glass, call John, and it'll start calling that person. So you have to have that person starred already in order to make a call to them, otherwise it would be kind of crazy to search through your whole Android contacts library. But that's pretty cool. Hands-free, you could be, you know, totally busy with your hands and not have any sort of control over your smartphone and still place a call to someone or send a message if it's important. And number 6, last but definitely not least, is the Google Search and Google Now. Now you guys already know how Google Search works, so I can say, okay Glass, Google, how long is the Golden Gate Bridge? And you guys already know basically how Google Search works, but it'll read the answer back to me. The Golden Gate Bridge is 8,980 feet, 2,737 meters, if that matters to you. So you already know how that works, and it works the same way that it does with Google Now on your phone. But Google Now on your phone also gives you sort of predictive search results and gives you relevant information wherever you go. Glass will do the same thing, so you can swipe through the Glass interface and view all this information where you'll need to know, the weather where you are, some translation data if you're in a different country, all kinds of different crazy things. The same way Google Now on your phone would do. But the bottom line with the Glass Explorer Edition is this. This is not the final version. This is not where you're going to be able to buy in a few weeks or months when there's a final version available. The final version is going to have updated hardware, it's going to have updated software, and it's going to have an updated price, because right now the Explorer Edition costs $1,500 in the United States for all Glass Explorers. Hopefully it'll be nowhere near $1,500 when it's finally mass produced. It'll hopefully be way less than half of that, but go ahead and leave what you would pay for Google Glass like this in the comments section below that like button. I feel like a lot of people would probably max out at around $500, maybe less, maybe $400 or $300, but we don't know what the price is going to be. But this is the Google Glass Explorer Edition. I'll have more videos on this to come. I have a lot more content that I want to show you guys regarding Glass and a whole bunch of other tech stuff. But if you enjoyed this one, definitely feel free to give a thumbs up below and be sure to subscribe to see more Glass coverage and more tech videos like this. Thank you for watching, and I'll talk to you guys in the next one. Peace.
So we've all seen holograms in museums and gift shops. They look beautiful, but we still can't go to the electronics store and buy that holographic television. So the question is, why hasn't that happened yet? Well, one of the main reasons is that a holographic television will require pixels many times smaller than what we can manufacture, even for our best mobile phones today. And so what we're trying to do in our laboratory at MIT is develop a 3D display technology that uses today's dominant display technology, which is liquid crystal panels, in a way that can create a beautiful 3D scene like a hologram.
As we move from two-dimensional displays to hyper-realistic multidimensional displays for 3D, for light fields, for multispectral and lighting-aware displays, the bandwidth requirements move from gigabytes per second to terabytes per second. But by using compressive displays, we can exploit compression not just in software, but also in optics, and bring those bandwidth requirements within manageable limits.
So what's our secret sauce? Well, if you look at the natural 3D world, say a white wall, it turns out as you move your head back and forth, that wall doesn't really change. And so what we do is we take compression algorithms, like you'd have in your digital camera on our DVD or Blu-ray. We look at the world, we identify these redundancies, and as a result, we can actually use liquid crystal panels with those large pixels to create beautiful 3D scenes that almost reach the quality of holograms today.
Here, the prototype is assembled in the directional backlight configuration. The front LCD layer sits atop a directional backlight, which is obscured while assembled. The LCD driver electronics are mounted with the panel on an aluminum plate. The plate is accurately positioned using a rail and clip system. From the side, the location of the directional backlight, composed of a uniform backlight, LCD, and lenses, can be more clearly seen behind the front LCD. Because of the close layer spacing allowed by the directional backlight design, our two-layer prototype has retained the thin form factor of an unmodified LCD panel. We now compare to the three-layer tensor display prototype. In this configuration, 3 LCD layers are illuminated by a uniform backlight. We choose a larger layer spacing to demonstrate the flexibility of the tensor framework and to avoid moire interference without the need for custom holographic diffusers. Displayed 3D images are perceived without any flickering, but when filmed with a high-speed camera, the temporally varying tensor decompositions are clearly visible for each of the 3 layers. So I think with new research, you always want to ask, why is this relevant now? And for us, we're taking advantage of two big trends in display hardware and graphics hardware. So the first is really high-speed display panels. And this lets us show a bunch of frames that your eye adds up together as a single coherent image. The other trend we're taking advantage of is really high-speed graphics hardware. So the chips that go into your laptop, your phone, or your desktop PC have become so fast in the last 5 years that we can solve a whole complex computational problem in the time it takes to show just one frame of video. And this has enabled a whole new way of thinking about 3D display.
There we go.
This was impossible until recently for Nikki, who was born without her right arm. But now, with the help of this multi-articulated hand, the very latest in next-generation prosthetics, she can perform even the most dexterous of tasks.
Using this day to day is actually really easy. It's such a simple mechanism for using it. I just control it with two sensors on the inside here, and those are operated with my muscles. So I flex one way to open it, and I flex the other way to close it. Just put it on like this, close it, open it.
This modern limb is only the second of its type to be used anywhere in the world. This hand is designed to look and work exactly like my hand. The reason nothing this complex has been produced before is because it simply hasn't been technologically possible. Nikki's hand has been specifically designed with women in mind. It has miniaturized components for true-to-life movements that allow her to carry out everyday activities.
It feels like something from a sci-fi movie. It's so exciting, and the possibilities of it and for future generations just feel endless now.
This limb, the best and smallest anywhere in the world, cost £30,000 to make. For Nikki, though, who can now do things she never could before, it's priceless technology. Luke Hanrahan, ITV News.